there isn't as much shielding there as we have here on Earth. Yeah, and then, well, hang on a second. So the two main reasons that someone would get exposure to radiation would be because they would have to get out of Earth and cross the Van Allen belts, which are a concentrated source of first neutron and then electron charged particles, and then cosmic radiation after they do cross that from gamma radiation. Yeah, so next slide, please.
Okay, so on the experiment, we're going to have two sensors, two radiation detecting sensors. The incoming radiation during the flight, it'll be focused onto the sensors. One of the detectors is not going to have any shielding at all, so it'll be more the controlled. And then the other one is going to have the shielding of our choice. We're looking into options that are flexible, that are trying to be sustainable, and reliable, able to actually shield the stuff, and lightweight, yeah. So as we go up, it'll be like the higher we get, we're gonna get like it'll be the radiation intensity is going to be measured as a function of altitude. So the higher we get, we're going to see different amounts of radiation, hopefully, and we're going to be able to test the effectiveness of the shield based on the numbers we get. So I think that's that. Yeah, next slide.
Okay. So there are some issues regarding our protection we're building. So first of all, we don't want it to be bulky and heavy, because the current generation of spacesuits are very hard to move in, not very effective on another planet or even in space. So a flexible and thin material would be ideal, and obviously one that blocks radiation so we don't fry our astronauts. One issue with radiation protection is you can't just block in the direction it's coming from, which in our case would be the sun and space, upwards, because there's an effect called secondary scattering where you might block the radiation coming in directly from the front, but when it hits your shield, it might scatter off and it could go and around your shield and hit your unshielded parts. So effectively, your entire object, your astronaut, your habitat, needs to be surrounded in some material that does its best to block radiation.
Next slide, please. So what we're designing is a 3D CubeSat to house this scientific experiment. We will be doing ground tests to test out the materials that we're looking into. The science department has agreed to provide us with some radiation sources, which is nice, in a safe way. And so we'll be testing on the ground, and we'll be using our sensors and calibrating them before flight. And once we do have our materials selected after the testing, we'll make a little box, and then so one of the sensor will go in, the radiation sensor will go into the box, and the other will be our control. So for this application, we are using an Arduino Pt1 as our microcontroller, and we are building a PCB separate of the avionics so that it does not affect the rest of the rocket flight or anything in any way. And so that was custom designed and built for the payload. Next slide. And then, yeah, go ahead.
Yeah, so we have a bunch of different sensors that we're going to be hooking up to the PCB. In particular, we have two radiation sensors that was previously mentioned, one for control, one for the actual test. And then we have, I believe, 6 thermoresistors. They're going to be positioned along the nose cone in sort of like an arc pattern, I guess, to measure the temperature gradient of the nose cone. Then we have 4 photoresistors, and they're going to be positioned around the nose cone as well to measure the spin of the rocket. We have a humidity sensor for the humidity. That's just to be sorry, I meant the pressure sensor is going to be a little pitot tube that's on the top of the rocket. That's going to measure the pressure as we go up through the atmosphere. And finally, we have a temperature sensor. Yeah, just to
yeah.
measure temperature.
Just an additional temperature sensor for inside the payload and the avionics bay. Next slide, please. So,
Yeah.
this is just a schematic of where the thermoresistors will be placed. So starting at the tip and then kind of going down along the profile of the nose cone.
Yeah, you can see that we expect a lot of temperature change at the top of the nose cone, and then not so much at the closer to the base. So we have a lot more sensors at the top and then fewer close to the base.
Mm-hmm. Next slide, please. And then, so like I mentioned, we did design our own PCB, and these are just some of the specs that go along with that. So Conrad was the one designing that for us. He did a great job, at least I think so. So yeah, we're going to be sampling data at 100 Hertz. We're using the Arduino TNC to be our microcontroller for this. And so it's kind of a PCB that could be used in the future for future payload experiments, just because it is fairly flexible to change up the connections that he has hooked up. If you can switch the side, you could have the schematic of the PCB. Next slide, please. Yeah, so here's just a schematic. Most of it's pretty straightforward. We have the thermoresistors, the radiation sensors, and then the only other thing is normally the Arduino TNC has a 3.3 volt output, but we also have a step up for some of our components that require a 5 volt output. And then the rest is pretty straightforward. Next slide, please.
Alright. So the payload is going to be set by CubeSat standards. It's going to be a base plate of like 10 by 10 centimeters. The height itself is going to be like 30 centimeters as well. As well, the payload has to weigh at least a minimum of 8.8 pounds, or 4 kilograms itself. And that's including with electrons, as Anna said previously. We're going to have like these containers. They're going to be fairly lightweight as well for the electronics, so add some weight. Finally, the plates itself are going to be 836 steel plates, generally. We're going to have like some steel plates. As well, we're going to have zinc-plated rods, about 30 centimeters long, along with steel zinc-plated hex nuts as well.
Yeah, so I guess the most important thing from the frame is that, unlike last year where it was too light, this year we are weighing about 7 pounds with our frame, so that leaves a good, just over a little bit more than 1 pound for the avionics and the radiation sensors and the rest of the experiments, which is good because then we're going to hit that weight requirement, which is something that is important to airframe and other tracking things. Yeah, so that's payload. Does anyone have any questions? Alex went first.
What sort of radiation samples do you expect to receive from the Faculty of Science? And what type of radiation are you specifically looking at?
Well, in flight, we'll be looking at gamma radiation. It's the only sort of cosmic radiation that'll penetrate as low as we are. As far as samples go, I'm not sure of the details.
Yeah, so we have been, well, do you mean sources, like radiation?
Yes.
Yeah, so we know we can get a photon source for radiation, and then we have 2 more contacts to talk about the charged particle sources. Yeah. So basically anything we want as long as it's feasible in the time from now to competition date.
If your goal is to look at cosmic rays, you may find that samples will only provide up to several mega-electron volts.
Mm-hmm.
So those will be in the X-ray range rather than inside of the gamma rays. And then the second question was, where will the radiation sensor be mounted inside of this frame? And do you expect to see significant blocking from the steel plates with respect to the radiation input?
Well, steel is not the greatest material for blocking radiation.
Yeah.
And as for the first part, the control will be in the top section of the frame. and the shielded sensor will be in the middle section.
And then the rest of the avionics, well, not avionics, but like
The
payload
rest of it.
avionics will be in the bottom section, yeah. So no, we don't expect the steel to get in the way, and the rest of the nose cone is radiation transparent, so it should be fine.
Perfect.
Yeah,
That answered my question as well.
okay. Yes.
For your sensors, are you using like a personal dosimeter type thing, or what is the sensor?
So we're actually looking at a couple of different sensors at the moment.
A lot of personal dosimeters tend to be rather large,
Yeah.
at least with all the casing around them. We have looked into, we've talked to, is it Aware?
Aware,
We've
yeah.
talked to Aware about getting a personal dosimeter without all of the bulky packaging around it.
Yeah,
Um,
that's kind of our fallback because it's a little bit more expensive than some of the other things, but it'll work for sure. So we're just gonna look around a little bit more. We have that and maybe another one that'll
Yeah.
work. So before we make any buying decisions, we're just gonna look around. Yes?
I may have missed it, but how does the payload structure attach to the rest of the rocket?
So airframe and payload are still working on that. Last time we talked about it, the threaded rods that we're using screw into the bulkhead. So that's like the
presented in the
primary.
airframe section.
Okay, sounds good.
Okay. Nice, yeah. Well, if not, then that was payload. Thank you for your time and attention. You can clap.
We're the recovery team. My name is Cheng-Yi. I'm Logan.
I'm Paula. I'm Tia.
Evan, Matthew.
Okay, and we're going to start off with the recovery sequencing, which is quite important in the recovery event. First off, the rocket reaches apogee after coasting, and at this point, a trigger signal is sent to the ejection systems that we have at the bottom of the parachute compartment, which is 2 CO2 charge cups. And next step after that is the pressure built by the CO2 charge cups will pop the nose cone off of the parachute compartment bay, and this will pull the drogue chute out of the compartment. This configurement will be like it for most of the descent, and once the rocket reaches 1,500 feet elevation, altitude, and then the next step happens, which is shown in the next page. So the main chute release mechanism, before securing the main parachute into the bay, now breaks, and this allows the drogue parachute to pull the main one out of the parachute compartment. And once the lines of the main parachute become taut, the force will continue to pull the main parachute out of the deployment bag, and then the parachute continues to inflate, and now we have steady descent all the way down to the ground. Yeah, next slide. Okay, so after we have the sequencing set out, we have to determine the forces that the rocket body and also the parachutes will experience. We used two different approaches. One was the infinite mass approach, which basically assumes that while at the initial velocity that the rocket is falling at,
the parachute opens instantaneously. So this will predict the highest amount of force on the rocket body tubes. The second method of finding the force is a modified version, which includes opening force coefficients determined by experimental data, as well as force reduction factors based on the canopy loading. So that relates the canopy open area with the rocket weight. We went with the former case, which is the infinite mass one, because it resulted in a higher number, and this gave us a bigger safety factor when we're dealing with the forces. So the drove shear parachute opening forces based on air density up towards 30,000 feet and a falling velocity of 180 feet per second, which roughly translates to 5 to 6 seconds of free fall for the rocket, gives us 1,900 units of force. And the forces experienced by the manned parachute, which happens at 1,500 feet with an initial velocity of 65 feet per second, give or take 5 feet, is 9,500 units. So we decided to keep it simple with the shock cord and just reuse last year's Kevlar cord, which is rated to 6,000 pounds. And yeah, next slide. Okay, so after determining the loads on the rocket, we then went on to develop the drogue parachute. So this kind of is in line with the main parachute as well. We found that the drag coefficient characteristics of parachutes relate closely with that of a flat plate and not of a sphere. So once the Reynolds number reaches a certain magnitude, the drag coefficient levels off. So with that in mind, we know that the drag coefficient doesn't change dramatically based on experimental data. So any numbers that we see with smaller parachute testings, we could extrapolate and scale up the values. So we wanted the descent rate to be, I guess, 65, 67 feet per second, around that area. And the drag coefficient we calculated for this particular dimension of cross parachute was 0.633. And this is based on the geometric porosity of the cross parachute. So how slender the cross is versus the nominal porosity of the cross parachute, which is how porous the canopy fabric is. And as for the canopy fabric porosity, that's measured in the amount of air that can pass through the fabric based on a certain set standard pressure. So based on the nominal porosity and geometric porosity of the cross parachute, the dimensions were chosen that allow a geometric porosity to have stability no matter the nominal porosity of the fabric. So that number came out to be 41.7% geometric porosity, which also directly relates the length and width of the cross parachute. So once this number was determined, we then went on to determine the nominal porosity to avoid any rotating instability. I forgot to mention that the geometric porosity was chosen based on oscillating instability and not rotating instability. With nominal porosity, that relates to rotating instability. So these two numbers were determined, and then the forces calculated from the last slide were used to determine the number of suspension lines needed, which we determined was 8 based on previous experimental data. We found out that increase in number of lines from 8 to 12 to 24 didn't really increase the drag coefficient too much, whereas it increased the weight a lot. So we decided to go with 8 suspension lines. And each of the suspension lines were rated at 400 pounds, which gave us plenty of safety factor, which was, I think, around 7 or so. And the 1.4 times length of the suspension line relative to the canopy diameter was chosen based on the trade-off between weight of the parachute compared with the drag coefficient. I forgot to mention that the cross parachute design was picked due to its superior stability characteristics and has been used for some parachutes already in the industry. And also, with the dimensions that we have and the materials that we're planning on using, the predicted weight of the drill parachute should be around less than a pound, although that number might increase in the future based on how many reinforcement tapes we need on the edges. Whereas last year's parachute was made out of Kevlar and it was 2.18 pounds. Okay. Then we went on to design the main parachute. Based on last year's model, the parachute was 24 feet in diameter. This year we decided to go with larger diameter, which was 26 feet. And the design we picked was a conical design. This design was picked at the beginning of the last semester, due to a trade-off between complexity of the parachutes and also the drag characteristics. So conical was picked because the bore dimensions was simple to manufacture, as we are manufacturing parachutes for the first time, and as well as the drag characteristics are better than that of a solid flat parachute. So the expected coefficient of drag for this type of parachute ranges from 0.75 to 0.9, and this all depends on a variety of factors such as vent and, of course, the suspension line length. The vent diameter was chosen to be 4.16 feet based on the commercially available parachutes out there, and as well as some of the experimental studies that was performed on the vent diameter versus the stability of the parachute. Suspension line length was chosen to be 300 pounds. This is based on the force calculations done earlier in the slides that predicted the force to be 9,500 newtons. And the suspension line length was chosen based on a trade-off study that we did balancing the drag coefficient versus the weight of the parachute. And as well, in literature it was recommended that at least 12 suspension lines, which relates directly to the number of cores on the parachute, should roughly be a multiple of 4 to prevent any uneven loading. Of course, most of the parachutes in this diameter usually go up towards 20 to 30 suspension lines, but we determined that the only difference that reducing the number of suspension lines made was the uneven distribution of the forces, which we could easily handle by sewing V-tabs to the lower lateral band where the suspension line is attached to the canopy, as well as the folding dimensions. Because the gore is wider, the folding of the parachute will also be, the resultant folded parachute will also be wider, but that could easily be jam-packed into the rocket body tube. As well, we picked this time a ripstop nylon, different from that of the drogue parachute, because the drogue didn't have a vent hole at the top, and we thought that with the vent hole, to increase the stability of the parachute, a zero porosity ripstop nylon would be doable, because zero porosity allows a higher coefficient of drag. Did I mention anything else? Oh, I guess I should have mentioned this in the last slide, but I forgot. the diameter of the drogue parachute was chosen based on the amount of drift that we'll encounter. So based on the data that Graham collected from a nearby airport in New Mexico somewhere, we took the maximum wind drift data from the month of June reported and used that to calculate the maximum predicted drift or historical drift that could occur for a rocket underneath a drogue of a certain diameter and coefficient drag. So the 8 feet that we've chosen should drift a maximum of 13 kilometers only, which is within the 16 kilometers allowed by the SOAR America Cup competition. And yeah, I guess next slide. Okay, parachute packing. As mentioned in the first slide, the main parachute will be packed into a deployment bag because sequencing of a parachute is very important. So we don't want the parachute to inflate before the suspension lines and the shock cords are taut. This way we increase or distribute the opening force over a longer period of time. And based on the dimensions that we calculated, hand packing density of a parachute is roughly 0.13 ounce per inch cubed. And based on the inner diameter of the rocket body tube, the length could be determined based on the packing density. And the main parachute will be packed in a zigzag fashion, right? Yeah, Z-folded fashion, which is basically first folding the parachute into that of like the gore shape. So imagine if you took an umbrella and you folded your umbrella up, you would have gores coming out like every single side. And then once that shape is attained, it would be farther folded, and then it would be zigzag folded and compressed into the parachute bag. After that, the suspension lines will be wrapped Z-folded again on the outside of the parachute bag, allowing it to be easily pulled out during deployment. The drogue parachute, we don't believe we would need deployment bag as the lines can be pulled out when the nose cone is popped off at a certain velocity. And yeah, next. Okay. The recovery ignition circuit is shown here. This is the full circuit of the initiation, well, I guess, system. And then the PVC rectangle you see on the bottom is enlarged, shown here. Garnet from the which team is it? Avionics did this circuit for us, and it's basically just a circuit that allows the charges to be set off when a signal is sent through. So as you can see here, the CO2 injection systems and the main separation systems would be loaded onto either load 1 or load 2. And because of the transistor being in an open state without a trigonal signal, it will be floating on those two loads. So the E-match, or the bridge wire, would not be set off in that case. And once the signal is set, then the loop is complete. And then once the current goes through the two loads, these two systems will be set off. So back to sequencing again, the CO2 systems will be set off at apogee, and then once the rocket reaches 1,500 feet, the main separation will happen, and that will complete the system. Looking back at it, the avionics is planning on using an 8-volt battery, which, based on calculations that we did, will roughly give us around like a 30 gauge wire at a 3.9 inch length made out of nichrome. This would give us effectively around 3 ohms of resistance and 2 amps of current. And based on the Joule's heating principle, we expect the auto ignition temperature of black powder to be reached in 1/3 of a second, hopefully. The competition also requires a redundant COT electronic system or flight computer. And that system runs on a 4-volt battery, so of course this value will have to be changed. So we will need 2 different E-matches, one for the commercially available flight computer and also the one for our avionics system. Yeah, next slide. Okay, and then going into the CO2 system here, based on last year's model, I think we used around 15 grams of black powder. And this required a fire blanket for the parachute and also caused a little bit of burn damage on the cords. So this year we thought that we might want to go with a more reliable system as well, because the black powder, once it operates at high altitudes such as 30,000 feet, the ignition is not as reliable as a rocket at 10,000 feet. So with a CO2 injection system, the black powder is contained. To give you a little background on how the CO2 system works, the CO2 canister is here in gray, and the system is up there in the red. The black and red wires are the load parts of the circuit that you saw earlier, and that leads to electric match, which is inside the red housing. Once a signal is sent, the E-match will light a little bit of black powder inside that compartment. And the reason that this is more reliable is because that compartment is airtight, unlike the black powder charges that were used last year. And once this black powder charge sets off, it will push a plunger that punctures the CO2 compartment and releases the CO2 at a fast rate, allowing the parachute compartment to be quickly pressurized and the nose cone to be popped off. After consulting with the distributors of the CO2 system, it was found that if we needed a CO2 system larger than 45 grams, then it's recommended that we use 2 because of the size of the canister. The flow tends to get choked and the pressure won't build up fast enough for the nose cone to pop off. So that's why we decided to go with 2 systems. Going back to the black powder charges used last year, it's recommended online that we go with a 5-to-1 ratio of CO2 to black powder. So if we use 15 grams, we want like 75 grams, I think, of CO2 to be used. And as well, as mentioned earlier, nichrome would be used as a bridge wire. And we would also want a primer on the E-match to increase the reliability of the ignition. So yeah, next slide. Okay. Now this is the main separation system that happens at 1,500 feet. Last year, a Jolly Logic chute release was used, and this is mainly used for smaller parachutes that, smaller parachutes that has a, smaller diameter, which allows this chute release to wrap around the entirety of the parachute and release once ejection happens. But because our main parachute is 26 feet, we're predicted 26 feet, this solution seems to be not viable. So we decided to go with a system that is used in, the rocketry today, and improve upon that to optimize it for our current rocket. And that is basically a 2-link system that separates in the middle upon initiation charge. And once that separation happens, it allows the drogue parachute to pull the main one out. Next slide. So as you can see here, this is the main separation system. You can imagine the system coming together with the 2 links on the other side going around the 2 outer holes, and then the top piece coming down the middle, preventing the links from separating. But once the black powder charge is set off in the middle hole, this will push the top piece out and also separate the links. Once this happens, the line attaching the bulkhead of the rocket to the core between the drogue and the main will separate, and then the drogue will pull the main one out of the body tube. Yeah. Is that the last slide?
Yep.
On the last slide there, where you showed the separation right there, that pin that's going to be shot out, is that attached to the rocket in any way? Is there going to be a wire going through that to keep it attached?
A wire going through the? Oh yeah, yeah. So like the piece that flies off on itself.
Yeah.
Yeah, we'll have a piece of like nylon cord loop around the middle, and then also the top piece. Cool.
What's the safety factor on the Kevlar cord right now?
Safety factor on the Kevlar cord?
Yeah.
Extremely high. 6,000 pounds. Yeah.
But what is the safety factor?
Let me see. You would take the 9,500 newtons, convert that to pounds, and
see, that's another thing. You guys do a lot of stuff in pounds and newtons, and we
Right.
can't do direct comparisons here. So
I think it was like 2,300 pounds.
2,300 pounds. Yeah. Yeah. So it's a safety factor of 3.
So what if your mains deployed at when the drogue should have deployed?
The main is deployed when the drogue is deployed?
Yeah, by accident.
Oh,
Will
then
you break
then
the
like
cord?
we would descend at the predicted velocity, but then it would take a lot longer to descend, so we would drift a lot farther.
But would the cord fail?
At the...
Because you have a lot more force with your mains.
Oh, you mean the suspension lines?
Yeah.
Oh, the suspension lines. Okay. We haven't calculated it, but I don't believe that the force will be too high, just because the increase of velocity is offset by the air density. The air density at like 30,000 feet is roughly like a fifth of that ground level.
So you guys remember there's a few rockets that came down last year without parachutes, like almost on us. And it was basically a big tube falling like 10 feet from us. So it does happen. Like I think you guys should definitely have that designed in and understand what your safety factor really is.
Okay.
Just a couple questions / comments on recovery systems. So first of all, you've got 2 CO2 chargers. Are those required in conjunction to separate the nose cone and deploy the drogue? Or are they?
Yeah.
They're not redundant charges.
They're not redundant.
So normally, and I don't know if it's different at this competition, but normally when you fly a rocket this size, you're required by law to have redundant recovery system, or at least redundant deployment. So what that would mean is you would have to have more than one attempt to deploy that drogue parachute. So in this case, I would think you would need 4 CO2 canisters, one to fire the first attempt, or the first pair that you've already got, and then a moment later, half a second maybe,
Okay.
and a secondary attempt. Because otherwise, if something goes wrong with that deployment, you're coming down ballistic.
Right.
And that's obviously dangerous. The other question I was wondering about is the attachment points for your recovery system. So that shock cord is obviously attached to the nose cone, and it's attached somewhere at the bottom of the bay where the parachutes are. Does it continue throughout the rocket, or is it stopping at a bulkhead?
Just stopping at the bulkhead.
So normally, again, because this is a very heavy rocket, and particularly the motor itself is heavy, I would recommend that you do something to attach that recovery harness directly to the CO2 tank on the hybrid motor, so that if everything rips apart, you're bringing the heaviest piece down with the main parachute attached to it. Because otherwise, you're dropping pieces. again, that's a failure scenario, but I would at least look into trying to design it so that you can attach your recovery harness to your heaviest piece, which is that tank. How did you select the 1,500 feet for your main deployment?
Oh, that's required in the rules.
That's in the rules? Because that gives you about 20 seconds to get your main deployed before you hit the ground at the speed you're moving. Deployment bags are not fast. That's probably, you still probably have a lot of time, but if you can, I'd be tempted to lift the height a little bit, buy you a little bit more time. Like 2,000 feet, it could probably give you about 30 seconds to get that main deployed, which is probably an eternity, but 20 seconds starts to, I've seen them, they take a long time and you're almost on the ground before you finally get a chute that big inflated, so that's just my thoughts. So.
Thank you.
Yeah.
Your loads on your parachutes were based off of your falling speed. You said the load on the drogue was based off 5-6 seconds of free fall. Was that taking into account your horizontal velocity as well from the flight after reaching apogee?
No, we didn't take into account any horizontal velocity, just vertical.
Okay, because it's very unlikely that they will be flying straight up and straight down. It's going to be flying sideways when that chute deploys. So it's not going to be purely vertical velocity. So you need to take that into account somehow.
Yeah, you're almost certainly going to have more horizontal velocity than vertical velocity, especially for the drogue event.
So sorry if I missed this, but so your first drogue parachute is activated through the avionics system, through the ignition. How does the second one get activated? How does the main parachute get activated?
Same way.
Okay, so avionics also sends a signal.
If everything goes to hell and for some reason the line that avionics sends is cut or it doesn't send a signal, is there any physical backup that doesn't rely on avionics systems, or is that a...
Yeah, the redundant system that we are planning on using is the egg timer. So that's the system that uses the 4-volt battery, and that itself will have the redundant charge. So like for all the systems that, here, we have 2 sets of wires going into each. So one will be the signal that the avionics system sends, and the second will be the one that the commercially available flight computer sends. So we have that redundant system. Just not the physical redundant system, but the electrical redundant system.
So looking at this design, I think there's a similar thing called a tender descender that works on the same principle. I'm wondering how this will be rigged together so that you'll be able to put your wires onto here, the wires that you're going to ignite the black powder charge with, and have the wires still be okay after deployment of your drogue.
Which wires are you referring to?
The wires that will be attached to this, like the electrical wires that will be attached to trigger the black powder charge for separation of the main.
So yeah, the reason we went and designed our own was because the tender descender had 3 different levels, one for small size rockets, one for mid-size, and one for large size. Unfortunately, the large size tender descender is no longer available. I think they either sold out and then stopped making them. So we decided to create our own, basically, level 3 tender descender. The way that we can prevent the line from breaking would be to have a lot of slack in it, more slack than the length of the Kevlar cord. So in that way, when it is taut, the line wouldn't snap or pull.
Is the main parachute bag just sitting slightly out of the rocket with this tender descender? Like with this design, which configuration are you guys going for?
Yeah, so the main parachute bag would be slightly, like it wouldn't entirely be out of the parachute compartment bay, whereas With this case, we think that it would reduce the shock load, whereas if the parachute was fully taut and the bag was hanging out of the parachute compartment bay, and that would decrease the time. So to answer your question, the parachute deployment bag is in the compartment bay before deployment.
So Jeff, are you keeping us on time?
Yeah, we're about 4 minutes past my planned time at the moment. Is that all for questions? Okay.
He doesn't bite. It's not a full moon.
Yeah.
All right, we good? All right, so my name's Keith. I am sub-team lead for the avionics system. We have Nathan here, who's actually Prez as well, that's helping out with the Kalman filter, which you'll see later. And we have Nara, who's working with our sensor design. We're missing a couple members, Garnet, who's been the hardware lead, along with Natalia, Evan, and Prithvi, and Aaron, who can't make it today for various reasons. So with that, let's get into it. All right, so the first thing we have in the avionics system is we have an embedded system, and we've got a digital rendering of the chip that we're designing. So we have custom made this chip. We actually took some designs that SolarCar had been using for their electronic system to monitor sensor data that they wanted, and we made some modifications to it so that it fit our needs. But got a lot of help from the SolarCar team and made the modifications, so we know that it mostly works from them, and we've actually managed to build said circuit, and it pretty much works. There's a couple minor errors which we have found workarounds for right now, but this is just our V1, so we will have a V2 which has all those little errors that we expect on a first version, hopefully worked out, so the second version will be working. So there's a couple different components that we've got on this. We have an IMU, an inertial motion motion unit. And this will get our accelerometer. We can detect rotation and magnetic field. We've got a barometer, which will act to help us figure out our altitude. A GPS, which we are using to track where the rocket actually physically lands in the desert, so that we can get these GPS coordinates and go drive and find the thing and put it onto a truck, so that we know where it is. We have some thermocoupler measurements just to collect some data, and then we've got SD card data logging. The data logging, for the most part, is not a necessity for this, but we want to start collecting some data, because more data that we have, we can analyze this after the flight and let any of the teams see what happens, maybe what the different accelerations that we got on parachute deployment were, or the speeds that we were hitting for the propulsion team. Frankly, it really doesn't matter too much to me what we're grabbing. We just want to make sure that the data we're grabbing can help the other teams for what they need in the future. So we have this dev board made, and our software team is currently working on actually programming it so we can start really collecting data and actually logging and saving it. And so our final board that I was talking about, this is just the V1. We have made the changes that we have from hardware errors, and we have found those workarounds. As the software team is doing their development with the V1 boards, we're waiting to get some feedback from them as they're continuing their development process to go, oh hey, it would be really nice if we could get this change, or this isn't working as we thought it would be. So once we get that set of feedback, then we're going to incorporate that into the V2 board, and hopefully all will be good with that. I also just wanted to mention on this that we are keeping in mind that with high accelerations and stuff, we want to be really sure that we secure everything properly. So you can see in the corners we've got nice spots where we can actually screw this board down. Wires we can make sure are really securely clamped in there, and we've been looking at various different connectors, so we aren't too worried about a wire coming loose in flight
at least not on this direct interface to the board. All right, next thing we have is power system. So we are going to have a battery that powers a couple things that we have, among them that development board, but also, as you'll see in a little bit, our communication system. And as we're sitting out there on the launch pad, we are going to have a power line in from the launch systems. And we're using this power in to keep the battery charged so that, you know, all is good and we can have a fully charged battery. But to do this, we need to make sure that everything is electrically good for that. So we're designing a small circuit which will basically take this power in and then regulate all the power in the couple different circuits that we're working with. So it's mostly meant to be sure that we are safely charging the battery. We don't overcharge or have too much voltage or something like that, and then it regulates our voltages and currents out so that we get a nice, safe, smooth power into our various systems and we don't have any weird spikes that destroy electronics. We have a couple different systems in there to basically idiot-proof it. One of the things I've kind of learned in engineering is someone's going to install it backwards or something like that. So we've kept that in mind with our design. We have Schottky diodes in a case it's placed backwards, and actually the LED indicators, they can tell us how the charging status is, if it's fully charged, and even if it's placed backwards. So if we do get it placed backwards, you'll have an LED saying it's backwards and nothing bad's going to happen in there. So, you know, hopefully under stress of competition, you know, someone can make a stupid mistake and it will be obvious and clear and no bad things happening because of this. We can take voltages up to about 13 volts in, which is good because we don't really need that high voltage, but it's nice to be a little bit safe on that. And we'll be charging 2 LiPo batteries for about 1100 milliamps. So, yeah. The other thing that we want to look at power systems is how much power is avionics actually going to use. So on the right over there, I've got sort of a diagram, and this is our absolute worst case scenario. And I'm pretty happy with this because what we've got is our radio transmitter, assuming it's continuously transmitting the entire time, which it won't be. We really don't need to continuously transmit for hours, just a couple small bursts here and there. But even if it did continuously transmit, at 750 milliamps, our GPS takes about 45 milliamps. The microprocessor that I showed you earlier with all the sensors, another 50 milliamps, and the SD card takes about another 60. This puts us at 905 milliamps. If we put in a 5,000 milliamp battery, so similar to what you'd see on like an RC car or like a drone or something like that, that gives us 5.5 hours. But if you look at this, one of the important things is that 750 is most of our total power consumption, and that's only if you continuously transmit. So if we, you know, the rocket is just sitting on the launch pad, we don't need to be transmitting there, and that's part of what software is going to be doing, is only transmit when we need to. When it goes and it lands somewhere, we don't need to transmit that entire time. So that 750 is more likely only going to be bursts of that for, you know, minutes at a time at most. Yeah, I think that's... Next slide. Avionics, our communication system, and I think out of all the systems we have, this is the only one that has a little bit of cause for concern. Now, what we really want to do is we want a nice plug-and-play system, something that someone else has figured out all this stuff, we just plug it in and we'll send it serial data. And we found a system up here, the JD RF900, and it's actually designed for UAVs and UGV telemetry. And this is great because what it allows us to do is just send serial data in, and via kind of magic, it comes out on the other side, and that's what you buy the system for, so you don't have to worry about a lot of that. It's got really nice range, so 40 kilometers, it transmits on the 900 megahertz bands, and you can go, you know, 20 to 30 decibels between about half an amp to full amp. So really nice, powerful radio that should give us great communication. The only real problem is it costs a couple $100, and if anybody has money that they'd like to donate to the club, please do, because we need this money. And right now, as much as I'd love to say we're going to get the system, from a financial set of reasons, I can't guarantee that right now. That's something that we have to really work out on the club's budget, where we can go. So keeping in mind that we might not get the system, which is nice and everything would work, we do have some backup plans that we're looking at. Last year had a system where they had a radio that went over, I believe, ham radio frequencies. We know that there are some errors and issues with it, and it mostly sort of worked, and so we're looking into how we can improve that system from last year, you know, getting the designs from them, looking at it, is there anything that we knew wasn't working that we can design around to make that better. We can go for that if we can't get the plug-and-play system we want. Additionally, the competition actually sticks their own electronics on board the rocket that will do some stuff on communication and figuring out how high we went. Now, we aren't supposed to touch this and we aren't going to touch it, but the nice thing is that if everything kind of goes to hell and no communications works, we still will be able to get the rocket back at the end because we'll be able to use this unit to find it. Now, that is definitely not ideal, but it is a potential backup plan that we know will be on board. Yeah, so if we can get the money though, this system is great. We've heard some really good reviews. Garnet, who is the guy who actually found this part, has had some friends who have used this and has gone on message boards, and we've heard really, really good positive things. So I'd like to be optimistic and hope that, over some sponsorship deals, we can get enough money to actually get the system. And even if we do get it a little bit late, because it's just plug and play and send serial data, it shouldn't be too hard to set up and get running. All right, so the most important part, I'd argue, of the avionics right now is the apogee detection. So the communication, we've already talked about what happens if nothing happens there, but we want to know when our apogee is so we can properly deploy our parachutes. And to do this, we have decided to start working on using a Kalman filter, which has been Nathan's main area, and he's been doing some stuff in classes on researching how this works. So most of this is his information that he's kind of told me about. So what we actually do is we look for apogee by detecting zero velocity. Now, acceleration, gravity, always constant, but you go up and you've got positive velocity, you hit zero, apogee, and then you start going negative as you start falling down. So we are looking for that zero, but we've also built in a little bit of a tolerance, and we do this because the Kalman filter isn't quite perfect, so we build a little bit of a tolerance for not quite zero, so that when we do get the deployment, that little fuzz factor of the difference between reality and the Kalman filter should keep us safe. We're using data from both the accelerometer and the barometer, and we do this because if we take just one of those sensors, we aren't going to get great data out because we're going to have some noise, we're going to have some errors in there. And if we just rely on one of these sensors, those errors, if we get a big spike in the wrong direction because who knows why, sensors do funny things sometimes, that big spike could be a problem and deploy something way too early or way too late. But by using both of these, we can kind of cancel out those errors and make sure that we're getting what we really want. So you can look up at the graph there, and the red fuzziness is the noise from the actual data coming in. Our actual altitude is in blue, and green is the Kalman filter. Now, some of you guys might know the boxcar filter, and while it does work, there's a lot bigger of a delay between when the boxcar filter detects its apogee and the Kalman filter. It looks like it's almost identical. You'll see on the next slide there's a little bit of a change, but it's really, really small, and for that very initial part where we go up, it's pretty accurate. So here is our actual apogee detection. So what we did is we actually took some data from the past. I believe this is 2015 launch data. So the raw data in orange is our actual, what we found. And then if we had had a Kalman filter on there, this is what we would have seen. And looking at the bottom axis, which is time, you can see that they almost line up perfectly. And the two pieces of raw data that are kind of important on here is you'll see a little bit of a spike at the very top and down at the bottom. And those are different chute deployments. So you're going to get a big spike on your acceleration as those kind of yank the rocket. And looking at that, where we saw that spike from the chute deployment and where the Kalman filter are, they almost perfectly line up. Now, as I said, the Kalman filter has a little bit of a time delay. So if we aren't looking for quite a zero, but just a really slow velocity, we can move the Kalman filter's trigger to just before the chute should deploy, and that's kind of what we're looking to get. The filter is going to return what we want for position, velocity, acceleration as a vector, and this just makes it a lot easier to work with. And he's been looking at the algorithm and seen this more and more commonly used to get these really accurate results, and uses a bunch of well-known trajectory equations.
What's your time delay? Right now it's about 2-ish seconds. I'm trying to fine tune it at the moment, so it's getting lower kind of as we go up forwards in time, and I'm fairly confident that we can get it to within a second by competition. Okay. Thanks.
Yeah, so with this, there's a couple areas of weaknesses. We know this and we're accounting for that. So the first thing is that slow deviation from the actual altitude, and that was what Graham just asked with what's our time delay. And this is what we're doing is we're building in that tolerance so that we can get it to delay at the proper time. Where is it? Sorry, that was second point, my wrong one. The other problem we have is that there's a deviation from actual data, and this happens as a factor of time. As the data kind of gets fuzzy, the error builds on itself, and so your error gets bigger with time. The nice thing is when you launch a rocket, it goes up really, really fast, so that error is not as big. It becomes bigger at the later stages, which we don't care about as much. For our future test plans, we do want to test this with pressure chamber simulation and get some more data sets to test with. We have our 2015 data, and that looks pretty promising for the applications we care to use it in. But of course, if we can look at other rocket launches with the actual data, we can put our Kalman filter on and see how it would have performed on a similar launch. And if we keep getting back these consistent results, that's good. But if we see something a little funky on there, we can look at that, try to figure out what the problem is. So, you know, if anyone here knows of other good data sets that we could use, it'd be really great that we can run that just to keep getting more trials to see how well this works. And yeah, I think that's it for the avionics. Do we have questions?
Well, we have a redundant trigger, right? If for some reason stuff goes wrong, you guys don't trigger the parachutes to release, we have that in timer thing. Is there anything we have to protect against stuff going wrong and deploying the parachute too early in the flight? Like if, say, the engine's still on or we're going up pretty fast still?
Frankly, I'm going to say it's more of a question to go to either propulsion or recovery.
We will have some software checks in there, so we'll make sure that acceleration is returned back to normal levels or within a tolerance of normal levels to make sure that the engine isn't still on. As for detecting when we're kind of coasting up to apogee, that's more tricky, especially with a tolerance. It's harder to tell if you're deploying at the right time and if you shouldn't deploy too early. But like I said, like Keith said, we're doing tests to double check that it is deploying at apogee, and we're trying different data sets where we go supersonic, don't go supersonic, trying to narrow down all of the possible things that could cause us to deploy early.
Again, more data sets is always better.
Yeah, I should mention as well, we do have data sets from other teams around Canada that we are testing this on. I'm trying to get more, so if you do have more, please let me know. But we do have a couple right now. Yeah.
So you're just using accelerometer and barometer data for your inputs to your Kalman filter?
Yes, we're using the accelerometer and the barometer. The accelerometer is immune to the pressure effects once you get closer to supersonic speeds, because your barometer pressure will spike and give you the wrong altitude. Your barometer is much more accurate for actual apogee because it doesn't have any sort of accumulating error from its measurements. So in between the two, plus your basic kinematic equations, the Kalman filter essentially takes an average of all three, and that smooths out any spikes, like you saw the parachute deployment from the black powder charges. That all got smoothed out.
Okay. So I was just curious if the static pressure measurements from the pitot tube on the front would be useful as well as an input.
We don't actually have a pitot tube right now. It's a little bit difficult to recover the rocket without damaging it. And since we're a little bit short on money, as has been mentioned, we decided not to include one this year because we don't have the budget to replace it if it does get damaged in a test flight or in transit. Yes?
We do have a pitot tube in the
Yeah. We do?
Yeah.
In the nose cone,
Okay, so my bad. I will chat with payload. I don't believe we have any. Do we have communication wires going from?
Right now, the only communication wires we have are going up the rocket or to the recovery system. Yeah. But you know, when I saw that we were getting the pitot tube earlier, it's one of those things that it might be nice to grab that data and see if we can use it. But that's.
We cannot. Anything that is on board for the payload cannot be accessed for the purpose of the flight. That's part of the competition regulations. So if it's on board our payload, it must be isolated. It must be isolated, and must be that they could replace it with birdshot, and we would fly the exact same. So unless your Kalman filter will be configurable to use both that pressure sensor and allow that pressure sensor to be empty, which is quite a bit of extra work. If it's part of the payload system, you cannot use it.
Other questions?
You guys got a vibration test your parts?
We would like to. This is, the more tests we can do on this, the better. As I said, we're definitely keeping in mind that vibrations, accelerations can knock wires out of place. So as we get to more final stages where we do have the software on the board working and we can get that power circuit working, we can wire it all up, a vibration test would be quite excellent. And I know that we've been looking at running some of these different types of tests, possibly in April or May when we've got a little bit more time.
But we're looking at other options that will produce vibrations as well. Yeah.
The communications module you're planning on purchasing, how many optional channels does it have, if any?
That would be
I want to say it's 12. I can get the numbers literally on my computer. I can get you that. I think it's 12.
It's on the order of 12 at least.
Yeah.
So there's the possibility that we could move off a channel if someone's using.
Yeah. Yeah. As you saw on the thing, there's a range of space that we can use, and I think it said 12 channels on there. But that's definitely something that we've kept in mind, and I know that Garnet's been looking at a little bit more.
Okay.
What's your data collection rate?
That needs to be tested. Right now we're looking at, I'm expecting somewhere in the range or on the order of 20 hertz. And then if we get any better than that, that's a conservative estimate. And then if we get any better than that, it improves our accuracy.
One of the things that we have to keep in mind as we're doing this is that it's a single core processor that we have on the board. So you can only run things in line, which means that we go through everything, we loop back to the beginning. So however long it takes us to do all the software side of actually the time to get data from sensor A, the time to get data from sensor B, and everything like that, we don't have the benefits of multi-threading. So the time that software takes to run that is something that I know that they're going to be keeping in mind to keep it as efficient as possible. But that total time to get through one loop is going to really kind of determine what our speed is.
Does your processor have a dedicated DMA? And does that DMA have access to the SD card?
I'm not sure. That would be a question for Garnet.
Okay.
Is there also a manual release button for the parachutes?
That was we don't have a manual.
There's complications with that because of competition rules. Because once you have two-way communication, you have to submit all your code to competition to have it approved, so that you don't have too much control over your rocket, and so that you're not stepping into missile territory. So we currently only have a downlink, or we're only planning for a downlink with the possibility of having a physical button later. But right now we have a plan to go through that certification process. Yeah.
I just want to mention Garnet is responding on the Rocket Team lead stack.
Oh.
So he's probably watching and responding right now.
He is watching. Did we get a response from him?
Yes, DMA.
Yes, DMA. Okay.
Okay, perfect.
The Keys question, the radio has 50 channels and uses a frequency hopping protocol.
Okay. Yeah.
Have you investigated if there is a possibility of overheating as convective cooling reduces with altitude?
Yeah, so we are actually looking at this, especially on our power circuit. I think we're trying to make sure that our temperature range is good for sitting in a black enclosed area in the New Mexico desert in the summer. So I think we're looking at maximum tolerances of 70 degrees Celsius. 60 would be nice, but I think we're designing for 70. As for it getting cold as we go up, we're again looking at the temperature ranges in there, but the nice thing is we are enclosed in the rocket, so we aren't going to see quite as much of the temperature as we would on the outside. We're closer to the engine, so you should get a little bit of heat on that.
What I would be worried about though is when there's low air pressure and you are enclosed, then it's less a worry about getting cold, but just building up heat because there's nowhere for it to go.
We don't have any heat dissipation in there, but again, we are definitely aiming on the side of electronics working on very hot. The big concern on that is just if you're sitting in the desert with the direct sun on, say, a black carbon fiber section, you're going to get some serious heat inside that. So
I want to interject here that say that all the body tubes are vented, so you'll get some airing from the outside when you're up in the cold temperatures, and you'll have some venting of the heat as well.
How are we for time?
We're sitting at 3:29. My break was at 3:30.
Before we go to break, did the data sets that you're testing, are they in supersonic range?
There's one data set that I have in supersonic range. The data set that we showed on here was subsonic, and I'm trying to get other supersonic data from teams here in Canada. I may reach out. We have some contacts with teams in Mexico now, so I'm going to reach out to them as well and see if I can get any more data sets. They don't seem
pretty important because of the transition.
There are, yeah. Or that is. So I'll be testing it extensively with the data set that I do have, and if worse comes to worse, I'll be generating my own code to simulate a rocket launch, as well as those pressure spikes. So then I can change the parameters to the worst case scenario or best case scenario for those pressure spikes from the supersonic flight.
any last questions here? All right.
Yeah. Is at the beginning you talked about maybe pressure testing this. Would it be useful to test it in a vacuum chamber, or is it only really useful if you combine it with your accelerometer?
Sorry, that's what we were referring to. We have access to a vacuum chamber with the physics department, so we'll be throwing it in there and running it. I probably won't disable the accelerometer. We'll be running it as if the accelerometer has failed to see how the system reacts and to see if we can detect apogee still, even with just the one sensor.
Okay, because we have a vacuum chamber as well if something goes wrong with physics.
Okay, thank you.
Yeah, and again, on the vibration testing, I'm not quite sure if anyone has sourced a place to do the tests for those. But if anyone knows of equipment that's open for us to do the vibration tests, that's definitely a set of tests I'd be very interested in running.
Do you have a range, or like a frequency range or a force range?
That's a question I'd be talking to Airframe probably on. It's not my area of expertise.
Sorry, what was the question?
Oh, just if we know what our frequency range for vibrations is going to be.
We do not. That's something we're still looking into.
Yeah, I'll keep in contact with Henry, and as we'll make sure that whatever tests we carry out will be done with him or someone else on the team. All right, in that case, I think we are on to break as our next session. So what time are we looking to come back, Jeff?
Break for 1 hour. And yeah.
Cool.